Hey folks, I'm still here. I'm going to do some math problems. I'm going to be working through division with complex numbers, so complex division, which the problem we'll be doing is on chapter 8 of Engage New York, number 2B. The page number is S30. What we're going to walk through first is finding the modulus, or absolute value. We're going to use a graphical demonstration to make sure we know what that is. Then we'll get into the multiplicative inverse and using the multiplicative inverse to do the division. And this right here is actually problem 2B. So you can skip ahead if you're good on those first two bits. So the modulus, or the absolute value, we use the absolute value symbol. So here I've defined z is some complex number that has a real component of 5 and an imaginary component of 2. So it's 5 plus 2i is one number, and that's z. I use these absolute value bars or pipes around z to indicate the absolute value or the modulus. And this absolute value is indeed its distance from 0. So from 0 out to where we've plotted z, this distance is the absolute value or the modulus. And so you can see right here we have a right triangle formed between the horizontal part, which is the real part, and the vertical part, which is the imaginary part. Those form a right angle. And so we're going over 5 and up 2. Here's 2, here's 5. So we can find this length using the Pythagorean Theorem, a squared plus b squared equals c squared, where we would have a squared could be the 5 squared, and b would then have to be the 2 squared, and we're looking for whatever c squared is. So we would have 25 plus 4 equals c squared. So c would be the square root of that. The square root of 29 would be c. Let's go back to the page before and do it without being able to also look at the triangle while we're doing that. So I have this component and this component. And so I would have the absolute value is going to be a long square root, and inside it I will put 5 squared plus 2 squared. And if I had negative 2 here, or 5 minus 2i as my number, then I would just use parentheses so that I'd make sure that I'm squaring it appropriately. And then this equals the square root of 25 plus 4, which gives us again the absolute value of z, or the modulus of z, is equal to the square root of 29. Square root of 29 does not simplify, so I'm done at this point. I have another video on simplifying radicals. So then we can find the modulus. That's going to be really helpful in a little bit, because we're going to use that to find the multiplicative inverse, which is how we divide. 2 has a multiplicative inverse of 1/2. This is just like what we went through in class. So if I have 8 divided by 2, that's the same as 8 times 1/2. So what can I multiply by in order to accomplish the same result as division? That's what the multiplicative inverse does. So what we're going to do is we're going to work out what number can we multiply by to achieve the same ends as dividing by 5 plus 2i. So let's try that. So let's see, we would have the 5 minus 2i here, and then I'm going to be multiplying that. So let's put parentheses around it so we don't end up just multiplying the negative 2i. And then I'm going to be multiplying that by 5. Well, that's wrong. Multiplying that by 1 over 5 plus 2i. And I can change this 1 over 5 plus 2i into not having any complex numbers in the denominator, so that I can just be doing multiplication and not have to deal with any division of complex numbers. I'm pointing at the division line that makes up a fraction. By multiplying it by its complex conjugate, which we've gone over in class, is the same value, but with subtraction on the imaginary component, 5 minus 2i. And so we'll see that is equivalent to, instead of going over 5 on the real and up to 2i, we're going to go over 5 on the real and down to 2i right here. And so we end up with something that is very, very similar to what we were working with for z. It is its conjugate. Its conjugate is always a reflection over the real axis. And then doing this out, I would still have this first part. And I'm developing the multiplicative inverse with this right here. So I'd have 5 minus 2i is from the original one here. And this one just so happened to come up with the conjugate as well. So I'd have times 5 minus 2i again from this piece over, and now I'm going to have 5 times 5, 5 times negative 2i, 2i times 5, and 2i times negative 2i. So that would be 5 times 5, 25, 5 times negative 2i, so minus 10i, 2i times 5, so plus 10i. Well, that's convenient, but we knew that was going to happen. And then minus 2 times I, minus 4i squared. Let's extend this line a little bit to cover everything. And we have these two in the middle that cancel out because one is added and one is subtracted. And we have this one over here has an I squared in it that can be simplified. So we would have equals this thing that we're trying to divide by some other number, and we end up multiplying by its conjugate of the denominator over here, over 25. This turns into minus a negative, so plus 4, 29. Hopefully that number looks really familiar. When we went back here and we found the modulus, it was the square root of 29. So what we're doing right here, when we find the complex conjugate and then multiply it, is we end up with the modulus squared. Taking away the square root is the same as squaring something. So we have then 5 minus 2i times 5 minus 2i over 29. So we can do this out. We could write squared, but I really want us to do it all the way out. So we'd have 25 is our first, and then minus 10i is that one, and then minus 10i again, because this is not times the complex conjugate. This is something times itself. And then negative times a negative gives us a positive 4i squared. That I squared is going to do something, and this is all over 29, because all we did was work on the numerator. So I end up with 25 minus 20i, and over here I get minus 4. So 25 minus 4 gives me 21, and minus 10i is minus 20i. Oh, I'm out of space. That's too bad. And all of that, maybe I have enough room to squeeze a 29 down in here. 29. I don't have enough room. Check this out. Let's expand the frame a little bit. Darn, not working. All right, looks like it's going to be parentheses over 29, which if I were to write as a single number, I would probably write as 21 29ths, because that way I have a real component, minus 20 29ths and I. And that would be my answer. Now let's show how would you do that quickly. Now that we know that when we find the multiplicative inverse, so this denominator can be replaced by the complex conjugate, so this is 5 plus 2i, and its conjugate is 5 minus 2i, divided by the modulus squared, which was this number squared plus this number squared. And it's always going to be adding the two squares together, regardless of this sign, because this sign is always going to be balanced by its conjugate having the opposite sign. All right, let's do that out quickly. So if I were to just see this one for the first time, 5 minus 2i, and knowing everything that I know over 5 plus 2i, let's do it. So this will be equal to 5 minus 2i times, all right, throw some parentheses on that, the conjugate of this, 5 minus 2i, and then that is over the modulus squared. So this squared plus this squared. So 25 plus 4 gives me 29. Yeah, I have the advantage of having done the problem before, but this gets pretty quick. And that's division. So I've just changed something that was division into multiplying by the multiplicative inverse. That's supposed to be an I. Sorry about it looking weird. And now I can proceed just using my multiplication skills like I learned to before. And that would be, again, 25 minus 20i minus 4 gives me 21 minus 20i. Again, the advantage of having done the problem before, over 29. Let's try this with a new problem. So that was 2b on page S30 in the Engaged New York one. Let's try 2c. And so yeah, you have these for free. So there's the square root of 3 minus 2i over minus negative 2 minus the square root of 3i. Well, they're throwing something at us there where they're going to have the same modulus. I wonder what that does. So that's equal to, I'm going to have this first part in parentheses, the square root of 3 minus 2i, because I'm not doing anything to that one. But I'm going to take this denominator and replace it with multiplying by the multiplicative inverse. So the multiplicative inverse is going to be the complex conjugate in the numerator. So I'm going to use parentheses so I don't get confused about the leading negative. So that negative 2 does not change sign. But this one, the imaginary component does change sign. So negative 2 plus the square root of 3i is my complex conjugate. And then in my denominator, I have the modulus squared, which is the first part squared, which would be 4. And the second part squared, square root of 3 squared is 3. And it's always added. Negative 2 times negative 2 is indeed positive 4. So we're good there. Now I can do out this multiplication here. So I'd have this times this times this, and that make sure that every part of each of these binomials is multiplied by every other part. So square root of 3 times negative 2 gives me negative 2 root 3. And then square root of 3 times the square root of 3i gives me square root of 3 times square root of 3 is just regular old 3. And then negative 2i times negative 2 is positive 4i. And then I have negative 2i times the square root of 3i gives me negative 2 root 3i squared, because I have I times I. I don't know why I get the big cursor sometimes. So negative 2 times the square root of 3, I times I. Negative 2 square root of 3i squared. And that is all over 7. The denominator ends up being the easy part of this. All right, so now let's see what do we have. I've got square root of 3i plus this, not square root of 3. I've got 3i plus 4i. So these two I can combine because they are like terms. This one, I have I squared, which I know is equal to negative 1. That's a negative 1 right there, being multiplied by this piece. So that makes this one positive. So I'd have negative 2 root 3 plus, right, or minus negative 2 root 3. So that part goes to 0. So I end up with 0 for a real part. Let's do that out. Negative 2 root 3. These two would give me minus negative 2 root 3. Then here I have plus 7i. Mm-hmm. And all of that is over 7. So then I would have these two add to 0. And I have 7i over 7. And this one miraculously reduces all the way down because I have 7 in the numerator and 7 in the denominator. Multiplying and dividing by 7 at the same time, they cancel to 1. So I'm left with just I. Box my answer, call it done. So that was division with a couple examples on complex division, where first we have to know how to find the modulus and know what a complex conjugate is, and then be able to combine those two skills to find the multiplicative inverse, and division ends up going pretty quickly with complex numbers. I hope you enjoyed the video, and please do reach out if you have any questions. I look forward to seeing you in class. Bye.